Hi students, now the topic is terrestrial telescope. This is exactly similar to the astronomical telescope what we had learned in the last class. Then the difference is, a simple and small difference is, in astronomical telescope we were having only two lenses. One is of large focal length, another one is of small focal length. In terrestrial telescope, we will be using three convex lenses of different focal length. What exactly the terrestrial telescope? Why we need to use, even though we are having the astronomical telescope, we will be discussing now. Let us start our discussion. The terrestrial telescope is to use to see the erect images of distant bodies on the earth. So this is the first most important point. We have used astronomical telescope to see the celestial bodies, right? To see the planets and the stars which has a far off distance. And the final image formed by the astronomical telescope was, in the last class, inverted with respect to the object. So if you are observing a planet, for example, which is almost spherical in shape, the final image you have got is inverted. The sphere, if you get as it is or inverted, there won't be much difference. But imagine from this point we are observing a tree which is at a far distance on the ground, on the earth's surface. If that tree image you get is as inverted, so there will be a problem to understand the properties of the image. So that is the reason the terrestrial telescope has come to get the final image as erect, that means as it is with respect to the object. So let us see the same thing I have written here. So the terrestrial telescope is used to see the erect images of distant bodies on the surface of the earth. This is the first advantage why we are using the terrestrial telescope over astronomical telescope. Now see, in terrestrial telescope, as I had already mentioned, there will be three convex lenses. Your objective lens and eyepiece will be common and similar in astronomical telescope. The same two objective and eyepiece can be taken in astronomical, so in terrestrial telescope even. See, the objective lens and the eyepiece is as this. When these two were there in astronomical telescope, what was the situation? As just now I told you, the final image formed will be inverted with respect to the object. So what is the lens we are introducing here? This is one more convex lens called erecting lens. What is this erecting lens here? This is the important one. So there will be an image formed by this objective lens. You know, that image will be erected by this erecting lens, and this image will behave as an object for the eyepiece, and the final image you get it as erect. Let's see. So before going into the topic, terrestrial telescope, let's quick recap the astronomical telescope. This is the astronomical telescope. In the astronomical telescope, there is an astronomical object. Final image is inverted image with respect to the object. So that is what I am going to do, a quick recap for you. So this is an objective lens. From an astronomical object, the light rays are moving parallel to each other and incident on it. When light rays are moving parallel to each other and incident on a convex lens, the image will form at its focus, and its point size are diminished, highly diminished. So the highly diminished image is obtained here, and this object, this image will behave as an object for this eyepiece. And see here, so the image formed by this is here. So object is somewhere here. So with respect to the object, the image is inverted here, right? So object we have considered like this, and the image is formed in this way, means that is inverted. It is inverted. As it is a celestial body, there won't be any problem, right? So, but we need the distant objects on the Earth's surface are to be erect and as it is. And before going into the deep concept of terrestrial telescope, and one more important thing. This is the case, we have assumed that the image, where the image is formed at least distance of distinct vision. So in that case, so the length of the telescope will be f naught plus ue when the image is formed at d. When the image is formed at infinity, then this ue will be equal to the focal length of this eyepiece, right? So f naught plus fe will be the length of the telescope. I hope you could recollect the last session. Now, let us start our major discussion called terrestrial telescope. In the terrestrial telescope, as I have mentioned, there will be three convex lenses. See, your own objective lens previously, your own eyepiece previously, what we had considered. So, in the middle of them, there will be a lens which is also a convex lens of a focal length f is kept here, which is of small aperture comparatively. These two means objective and eyepiece. Now, how the image will be formed? What will be the magnification in this situation? Let us learn. There is an objective length of focal length f naught. Object is at infinite distance, right? So, our far of distance, whenever the object is at far of distance, we will take the light rays coming from them are parallel to each other. So, the light rays are parallel to each other and incident on your object length. What happens? The image will be formed at its focal length. Where is the focal length of it? See, f naught. The image is formed here. It's fine. A dash, B dash is the image. Right? Now, we will adjust this lens. This is the lens called erecting lens. And this erect lens will keep it a point such that this image will behave as an object for this erecting lens and kept at 2f distance from this erecting lens. That's the interesting part of this. So there won't be any magnification produced by this one. We don't want the magnification to be produced by this one. We need only the erect image at the end with respect to the object. That's the reason. So this is the image is formed by this, right? So this image will behave as an object for this, and where the object is kept now, see here at a distance of 2f. Look at here. At a distance of 2f means 2 times the focal length. So this is the convex lens, and object is placed at a distance of 2f, and definitely image also will form at a distance of 2f, right? Image will be inverted. So if it is an object, its inverted image will be here. You can see that is also formed at 2f. That is also formed at 2f, right? So the total distance between the object and the image in case of erecting lens will be 4 times f. You can see here. So this is 4 times f. Now, I have an object here, and this is the object is placed between focal length of the eyepiece. There is a focal length of the eyepiece. Focal length of the eyepiece and optic center. You can see here. Focal length of the eyepiece and optic center. Between this object is placed. Now, where the image is on, where the image will be formed. So you know the image will be formed somewhere here. So this is A double dash and B double dash. And this is the case we had already discussed. A double dash and B double dash here. So this is the case I had considered that the image is forming at least a distance of distinct vision. Right? Now, object is somewhere here. With respect to the object, you see the final image, it's erect. With respect to the object, you identify the final image, it is erect. And with respect to the object, you identify the final image, it is inverted. So that is the important point why we had considered the terrestrial telescope. Right? So what is the function of the erecting lens? Commonly asked subjective type question in your board exams. What is the function of this erecting lens here? Number one, it will only erect the image formed by objective lens. Right? So this is the image, it is erected by this convex lens, and image is here. That means this will behave as an object for this eyepiece, and final image formed here, so which is erect with respect to the object present somewhere. Now we need to concentrate on two important things now. Number one is length of the terrestrial telescope, and number two is magnification of the terrestrial telescope, called magnifying power of the terrestrial telescope. And let's begin. Now, when the image is formed at least distance of distinct vision, in this case, let us identify the length of the telescope when the image is formed at D. Tell me, what is this? F0 plus 2F plus 2F, you can see. F0 plus 2F plus 2F plus object distance. See here? So this is the object distance. Understand? This is the object distance. So this is what length of the terrestrial telescope when the image is formed at D. So when the image is formed at infinity, the length of the telescope will be, this will not change, it is F0 plus, and this 2F will not change, plus this 2F also will not change, but the change will be here. The image will be formed at 2F. In that case, we will adjust that the image will be forming exactly at the point of focal length of the eyepiece. You know, for the convex lens, when the object is kept at the focus of it, the image will be formed at infinity, right? So we will make this erect image to be placed exactly at the focal length of this eyepiece, so that the final image will form at infinity. Then this object distance for the eyepiece will be focal length of the eyepiece. So that is the focal length of the eyepiece. So this is the normal adjustment. So this is called a normal adjustment. I hope you remember, in case of astronomical telescope, we had discussed about the normal adjustment. Normal adjustment means the image is formed at infinity. In all the telescopes, the normal adjustment definitely will be the image is forming at infinity. So let's talk about the magnifying power. Magnifying power in this case is exactly similar with astronomical telescope. Same like as astronomical telescope. In astronomical telescope, the magnifying power when the image is formed at D, least distance of distinct vision. So it will be F0 by Fe into 1 plus Fe by D. What is F0? Focal length of the objective lens. What is Fe? Focal length of the eyepiece. And what is D? 25 centimeters. When the image is formed at infinity, the length of the telescope will be like this. F0 plus 2F plus 2F plus Fe. And the magnifying power will be similar like astronomical telescope, F0 by Fe. That's it. Right? Now, there are some disadvantages with this terrestrial telescope than astronomical telescope. What are the disadvantages? Let's see. It's so simple. What are the disadvantages? Number one, the length of the telescope will be increased. So previously the length of the telescope, imagine in the case of normal adjustment, length of the telescope when the image is formed at infinity, F0 plus Fe, right? So in the case of normal adjustment, let us compare astronomical telescope and terrestrial telescope. Astronomical telescope, if it is F0 plus Fe. For terrestrial telescope, normal adjustment you see. F0 plus Fe is as it is, but in the middle you see the term called 4F, right? So that indicates length of the telescope is increased by 4 times the focal length of what? Focal length of objective lens, or focal length of eyepiece, or focal length of the erecting lens. The third option is correct. Focal length of the erecting lens. So focal length of the erecting lens is f, right? So the length of the telescope is increased by 4f, where f is focal length of the erecting lens. In case of terrestrial telescope, that's the first disadvantage, right? So let me write here disadvantages. Number 1, length will be increased by 4f, right? Here itself. The second disadvantage will be the number of refractions taken by the light ray is increased. Here there is a refraction, 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 here refraction, here refraction, right? So the light ray will be undergoing the phenomenon of refraction 1, 2, 3, 4, 5, 6 from the 6 surfaces. So when a lot of refraction taking place, the intensity of the image will be decreases, right? So that is what I am writing here. So the brightness of the image, decreases as more refractions are taking place. So this is the concept of terrestrial telescope, and with comparison of astronomical telescope we have learned here. These are the two types of telescopes called refracting telescopes. So the construction will be difficult, costly, and there will be defects in this image formation by these telescopes. That's the reason. There is a reflecting telescopes concept is also arise. This is what two types of telescopes are refracting. There is no reflection involved here, right? So now, to avoid the cost difficulties, manufacture difficulties, as well as to avoid the defects in the image formation, there are two types of reflecting telescopes as also discovered. So those reflecting telescopes, we will be learning it now. Let's start. Reflecting telescope. What we have discussed, to eliminate the manufacturing cost and defects of the image form, we have introduced another type of telescopes called reflecting telescopes. And in this reflecting telescopes, objective lens in case of astronomical and terrestrial telescope will be replaced with a paraboloidal mirror, right? So this is a concave mirror we will consider. Concave mirror, parabolic shape, having a large radius of curvature and large focal length, also similar to our objective lens. And the eyepiece will be as usual. Whatever the eyepiece we have used in astronomical and terrestrial telescope, same eyepiece will be there, a convex lens, right? So here the system will be the combination of a mirror and the lens. In the refracting telescopes, the system will be the combination of either 2 convex lens or 3 convex lens, depends on the requirement. Let's start. There are 2 types of reflecting telescopes. Number 1 is Cassegrain telescope and the second one is Newtonian telescope. Depends on the situation, and to see the particular object we will be using any one of these. Cassegrain telescope, there will be a concave mirror which is parabolic shape here, and there is a hole middle of it. But its radius of curvature will be same. There will be a convex mirror is also there. Imagine there is an object at infinity. We are observing an astronomical body. Light rays are moving parallel to each other. They will be reflecting. Before they meet each other at some point, we have kept a convex mirror here, which is a diverging mirror. See the diverging, these two reflected rays and meet at one point actually. So these are the two light rays, reflected light rays meeting at one point, right? So when it is meeting at one point, the real image will be formed, and that is what the real image is observed through these eyepiece, right? In both the cases, that may be Cassegrain telescope or Newtonian telescope, the image will be formed at infinity. In both the cases, we will consider the normal adjustment only. So this is how we can see the astronomical bodies. The same way, Newtonian telescope. Newtonian telescope also will have a concave mirror. Two light rays will be moving parallel to each other and incident on the mirror. As your concave mirror is converging mirror, it will converge the light ray. See, this is the first reflected ray and it is the second reflected ray. Here, we will be keeping a plane mirror. And you know, this is the plane mirror as you can see in the diagram. This is the plane mirror is not kept along vertically or horizontally. And this is the plane mirror is kept at 45 degrees as from the length of the telescope. Imagine this is the length of the telescope. The angle between the length of the telescope and the plane mirror is 45 degrees. Remember here 45 degrees here theta value. What is the theta? It's the angle between axis of the telescope. This is the axis of the telescope and the plane mirror, right? And this is what the incident point. According to the normal and laws of reflection, this will be the reflected light ray. And this will be the incident light ray on the plane mirror again. And according to laws of reflection, there will be a reflection takes place here. So these two reflected rays are meeting at one point. You can see here. Here also there is a real image will be formed through the eyepiece. We can see the image formed at infinity because the normal adjustment I have told you. So this is the eyepiece. Right now, what is the focal length of your concave mirror? Focal length if they give or not, radius of curvature they will definitely give you, and the focal length of the mirror which is equal to radius of curvature divided by 2. And what is this focal length of the mirror and why the mirror focal length we have considered? So I have written clearly here, in reflecting telescopes, objective lens will be replaced with paraboloid mirror, that means concave mirror here. So this can be considered as your focal length of the objective lens while solving the problems. So focal length of the objective lens and focal length of the eyepiece will be given definitely. So in these cases, the magnification, how you get it, whatever may be, that may be your Cassegrain telescope or Newtonian telescope, the magnification will be equal to focal length of the objective lens by focal length of the eyepiece. So focal length of the objective lens we have got already, R by 2, R if they give focal length of the mirror. So that will be the focal length of the objective lens. And from here, you can find the magnification of the reflecting telescopes. Well, maybe this one or the Newtonian telescope. Let us solve few basic model of numericals related to the terrestrial telescope and reflecting telescope. A terrestrial telescope of focal length of the objective lens is given 180 centimeters. Objective lens focal length must be more. We had already discussed. Focal length of the eyepiece is 5 centimeter. And in terrestrial telescope, we have kept an erecting lens, right? The erecting lens has a focal length of 3.5 centimeter. what is the separation between the objective lens and eyepiece? That means length of the telescope they are asking. What is the magnifying power for the normal adjustment? Magnifying power for the normal adjustment. So that means they are asking the length of the telescope also for the normal adjustment only. Can we use this lens to view the astronomical bodies? Most of the students may be having confusion that this terrestrial telescope, can we use it to see the astronomical bodies? Or astronomical telescope can I use to see the distant bodies present on the surface of the earth? So this is a common doubt, and let us discuss this. So what is the first part here? So the length of the telescope is equal to, so what is the length of the telescope in this case? When the image is forming at infinity, f naught plus 2f plus 2f plus fe. I hope you remember this. Now f naught plus 4f plus fe. Let's write. N is equal to, what is f naught? 180 centimeters plus what is 4 times into f? F is the focal length of the erecting lens. It's 3.5 here plus focal length of the eyepiece is 5 here. So this is 180 plus, so this is 3.5 into 4. So that will be 14 plus 5. So what I can write here, it's 194 plus 5. It's 199 centimeters is the length of the telescope. That means the distance between objective lens and the eyepiece. Now, what is the magnifying power? Magnifying power in the case of normal adjustment, we know f is equal to, m is equal to f naught by fe. So what is f naught? It's 180 centimeters divided by, what is focal length of the eyepiece? It's 5. So how much it will be? This is 5 threes, here 3 is there, so then 5 6. So it is 36 is the magnifying. Now the last question. What is, can we use this telescope to view the astronomical bodies? Definitely we can use, but I have told you already, the brightness of the image will affect because of the more number of refractions. In astronomical telescope, there are 2 lenses through which refraction taking place, but here there will be 3 lenses refraction is taking place through. So the brightness of the image will be decreases. More refractions, brightness of the image will decrease. More reflections, brightness of the image will decrease. So that's the answer for this. Now, a reflecting telescope has a concave reflector of a radius of curvature 120 centimeters. So, focal length of the mirror is equal to 120 by 2, which is equal to 60 centimeter. Can I write the 60 centimeter is focal length of the objective lens? Yes. Focal length of the mirror will behave as a focal length of objective lens here. Now, calculate the focal length of the eyepiece to secure a magnification of 20. Magnification is 20. So 20 is equal to, so I have told you already, in case of reflecting telescope, we will be considering the magnifying power as the image is formed at infinity only. So magnification m is equal to f naught by fe. So we have f naught 60 by fe. So what I can write, 0 0 cancel 2 3s. So focal length of the eyepiece will be 3 centimeters, and here also one condition is satisfied. Focal length of the objective lens must be more than the eyepiece. Yes, focal length of the objective lens is 60, eyepiece focal length is only 3 centimeter. In this way also you can check whether your answer is correct or not. So dear students, this is the end of ray optics and optical instruments chapter. one of the biggest chapter in your 12th standard syllabus, as well as important chapter in your 12th standard syllabus. The minimum number of questions you get from this chapter is 2 and maximum will be 3. Trust me, generally 3 questions from this chapter are usually asking in your previous NEET exams. So the number may be same or more in your NEET exam. And each and every concept in a detailed way and in the easiest method we have learned the complete chapter. I have already given you the assignment. Some more questions will be given for you as assignment. You just start doing them, and any doubts at any point of time, your Anand Academy will support you always, forever. In the next classes onwards, we will be starting a chapter called Current Electricity. And this is the current electricity also is one of the important and major chapters for your NEET exam. All those.